On November 23, 2023, a detector in the United States picked up a signal. It lasted about 1/10 of a second. Most people on Earth were asleep. But in that 1/10 of a second, 7 billion light-years away, two black holes that our physics said should not exist collided with enough force to shake the fabric of space itself. The ripples from that collision traveled for 7 billion years, longer than the age of our solar system, crossed the entire observable universe, and arrived at our planet as a distortion in space-time 1,000th the size of a proton, and we measured it. That alone is extraordinary. But what made this signal different is that it broke a rule we thought was unbreakable. In physics, there is a range of black hole masses that our best models say cannot exist. We call it the mass gap. Both black holes in this collision fell squarely inside it. This is the story of how we found the impossible signal, what it took to detect it, and what it's forcing us to rewrite. To understand this signal, we need to start with Einstein, specifically with a prediction he made in 1916 that he himself believed could never be tested. Einstein's general theory of relativity tells us that mass warps space-time, the four-dimensional fabric of the universe. Heavy objects create depressions in this fabric, like a bowling ball on a stretched sheet. But Einstein went further. He predicted that when something massive accelerates through space, something truly massive, moving extraordinarily fast, it should create ripples in that fabric, waves in space-time itself, gravitational waves. Einstein thought these waves would be so small they could never be measured. He was right about the size, but he underestimated human ingenuity. In 2015, 60 years after his death, we measured one. A collision of two black holes 1.3 billion light-years away caused a ripple that stretched and compressed a 4-kilometer detector by less than 1,000th the width of a proton. We detected it anyway. LIGO, the Laser Interferometer Gravitational Wave Observatory, is one of the most precise measuring instruments ever built. Two detectors, 3,000 kilometers apart across the United States. Each one a pair of tunnels, 4 kilometers long, meeting at right angles. At the end of each tunnel sits a mirror, polished to sub-nanometer precision, suspended from fused silica fibers to isolated from seismic noise. LIGO fires lasers down these tunnels and measures the exact distance between the mirrors. When a gravitational wave passes through, space-time contracts in one direction and expands in another. The tunnels change length by that proton fraction amount. The laser pattern shifts. LIGO reads the shift. Since 2015, the LIGO-Virgo-Kagra collaboration has detected over 300 black hole mergers. In 2017, its founders won the Nobel Prize in Physics. It has revolutionized our understanding of black holes. And then, in November 2023, it detected something that made even LIGO veterans stop and stare at their screens. The signal that arrived on November 23, 2023, was designated GW231123. It lasted about 1/10 of a second. It was 20 times louder than typical detector noise, and it showed up at both detectors, separated by 3,000 kilometers, within the time it would take a gravitational wave to cross that distance. To rule out a fluke, the team ran simulations of thousands of years of fake data. They found that random noise could mimic this signal less than once in 10,000 years. It was real. So they did the math. 7 billion light-years away, two black holes had merged to form a single black hole with a mass somewhere between 182 and 251 times our Sun. Before this event, the most massive black hole ever seen after a merger was about 140 solar masses. GW231123 shattered that record by nearly 80%. At the moment of collision, it was the brightest event in the entire universe. It released 15 solar masses worth of energy, purely as gravitational waves. That's nearly 3 followed by 48 zeros joules. More energy than every other star in the observable universe combined was producing at that exact moment. And it took 7 billion years to reach us. But here's where the real mystery begins. When scientists analyzed the signal further, working backwards to determine the masses and spins of the two original black holes, what they found should have been impossible. Both black holes sat in what physicists call the mass gap, a range of masses our best models say black holes cannot occupy. To understand the mass gap, we need to talk about how black holes are born. When a massive star exhausts its nuclear fuel, it can no longer generate the outward pressure needed to balance gravity. The core collapses. The outer layers rebound in a cataclysmic explosion, a supernova. If the remaining core is dense enough, it keeps collapsing, forming a black hole. This process typically produces black holes up to about 50 solar masses, and supermassive black holes, millions to billions of solar masses, are thought to grow over billions of years at the centers of galaxies. But in between, black holes of roughly 50 to 130 solar masses, the intermediate range, were predicted to be impossible. Here's why. Stars in that mass range don't produce the right kind of supernova. Stars between 130 and 250 solar masses either explode so violently they leave no remnant at all, or they shed so much mass before dying that what collapses is too small to reach the mass gap. The mass gap was supposed to be empty, a forbidden zone in black hole physics. For almost 10 years after LIGO began operating, that seemed correct. Hundreds of black hole mergers, none in the mass gap. Then GW231123 arrived. The two black holes involved, 103 and 137 solar masses, both inside the forbidden zone. Our theory was wrong, at least in some cases. The question was, why? The first explanation scientists considered was the simplest. Maybe these black holes grew through a series of smaller mergers. Each time two black holes collide, the result is a larger one. Do it enough and you can reach the mass gap. It's a plausible idea. We know this process can happen. In dense environments like globular stellar clusters, black holes can interact frequently with high enough escape velocities to prevent the merged remnant from being flung out of the system. But there's a problem. When two black holes merge, they combine not just their masses, but their spins. And since those spins are in random directions, they tend to cancel each other out. Each successive merger should reduce the spin of the resulting black hole. The two black holes in GW231123 were spinning at nearly the speed of light, among the fastest ever detected. If they had grown through multiple mergers, they should have been spinning far slower, not faster. GW231123 wasn't just the most massive black hole binary ever detected, it was also the fastest spinning. Those two facts together ruled out the simple merger chain explanation. Something else had to account for their mass. Something that could produce a heavy, fast-spinning black hole. Something that happened when these black holes were born. The answer, according to a team at the Flatiron Institute's Center for Computational Astrophysics, may have been hiding in one of the most overlooked features of massive stellar collapses, the parent star's magnetic field. This might sound abstract at first, but magnetic fields turn out to be one of the most powerful forces in the environments around collapsing stars, and we have been dramatically underestimating their role. The team, led by researcher Ore Gottlieb, started with a 250 solar star. They modeled its entire life, from the first hydrogen it burned to the moment its core gave out. By the time it died, it had burned through much of its own mass as fuel. The collapsing star sat at around 150 solar masses, just above the mass gap, not quite there yet. But then the supernova happened, and the magnetic fields took over. Here is the mechanism that changes everything. When a rapidly spinning star collapses,
The infalling material doesn't just fall straight in. It forms an accretion disk around the newborn black hole, a swirling disk of superheated gas and dust. And as that disk rotates, the magnetic fields threading through it get wound up, tighter and tighter, like a coil spring being compressed. When magnetic field pressure becomes strong enough, it launches material away from the disk, outward, away from the black hole. In extreme cases, it forms relativistic jets, beams of plasma blasting outward at near the speed of light. We've seen this exact process in quasars and active galactic nuclei, the blazing cores of distant galaxies where supermassive black holes are actively devouring matter. In the simulations, the stronger the magnetic fields, the more material they blast away from the black hole before it can be consumed.
With very strong magnetic fields, up to half of the star's original mass can be ejected rather than accreted. This is how you stay inside the mass gap, not because you started small, but because the magnetic fields prevented the black hole from eating too much. But the magnetic field story has a second chapter, and this one explains the spin. Every time the magnetic fields generate one of these explosive outbursts, every time a jet fires and mass is blasted away, the explosion imparts a tiny kick to the black hole, a push, a nudge. Physicists call this a stochastic natal kick. Each individual kick is small, but if the timing and direction are right, if the kicks reinforce rather than cancel each other, they can spin the black hole dramatically faster. This creates a direct, testable relationship between the mass of a black hole and how fast it spins. Strong magnetic fields, more material ejected, lighter black hole, slower spin. Weak magnetic fields, less ejected, heavier black hole, faster spin. The two black holes in GW231123 were both heavy and fast spinning, exactly what the model predicts for moderate magnetic fields. The simulations matched the signal. There's more. The model also predicts an observable signature. Those magnetic field-triggered explosions should generate short, intense bursts of gamma radiation, similar to gamma ray bursts, but with a specific profile. If we can find these gamma ray signatures associated with black hole mergers, it would confirm this formation pathway and tell us how common these impossible black holes really are. So what does GW231123 actually change? First, the mass gap is not empty. We now know that black holes in this supposedly forbidden range can form. We don't know how common they are, but we know they exist. That means our model of how black holes form from massive stars had a gap, and we were filling that gap with an absence rather than an explanation. The mass gap wasn't a fundamental law of physics, it was a limit of our models. And the thing that was missing from those models were magnetic fields. Second, if the connection between mass and spin holds, it becomes a new diagnostic tool. Every time we detect a gravitational wave signal, we can use the mass and spin of the resulting black hole to infer the magnetic field strength of the star that created it. We would be reading the gravitational history of stars from the gravitational echoes of their death. Second, the next generation of detectors is coming. The Einstein telescope in Europe, the Cosmic Explorer in the United States. Detectors 10 times more sensitive than LIGO, capable of detecting black hole mergers across virtually the entire observable universe. These instruments will hear thousands of signals per year. Some will be in the mass gap. Some will have the high spin signatures that match this model. Some will have the gamma ray counterparts we're now looking for. GW231123 didn't just break a rule, it gave us a new map for what to look for, and the tools to look for it are already being built.
A tenth of a second. 1,000th the width of a proton, 7 billion light years. In that signal was the record of two black holes that shouldn't have existed, colliding in the most energetic event in the observable universe at that moment, and traveling across more than half the age of the cosmos to arrive at a detector in Louisiana. We didn't just detect the impossible, we found out why it was possible all along. The mass gap isn't a wall, it's a window, and on the other side, hiding in the magnetic fields of dying stars, waiting to be born in violent collisions we're only beginning to understand, there are black holes we haven't imagined yet. GW231123 is just the first one we've managed to hear.